What's up, team? Today we're talking about the triangle proportionality theorem. First, some quick review. Recall that if we have two parallel lines, in this case it's given that line A is parallel to line B, and you have all these different angles here. There's a bunch of angle relationships that are created here. We're going to focus on corresponding angles. So in this case, notice that angle 1 and angle 5 are congruent to one another because they lie on the same space on their parallel line as it relates to the transversal. Similarly, angle 2 and angle 6 are corresponding, as are, how do I differentiate this? 7 and 3 are corresponding, and lastly, make this one squiggly, angles 4 and 8 are corresponding. So not all those are corresponding to each other, but the pairs are. So 1 and 5, that's a pair. 2 and 6, that's a pair, etc., etc. So we're going to use that idea with our triangles. Okay, the new stuff. So here's the problem we're going to focus on first. Our goal is to find the length of AD. Right now it's 15 plus x, but we don't know what x is. So of course we're going to find x, add it to 15, boom, game over. But what's going on here that's different than some of the other stuff we've studied is we have a triangle, kind of like a little triangle within a bigger triangle, and the two bottoms, the two bases of these triangles are parallel to one another, and that's given. So that's a big deal. So because they are parallel, we're going to use the idea that we just reviewed a minute ago. So if the line BE and CD are parallel to one another, then you can say AD would act as a transversal, making these two angles congruent to one another. It's the same idea we just discussed. In the same way, line AC acts as a transversal, a separate transversal to the same two parallel lines, making these two angles congruent to one another. Now, we see pretty quickly in our two triangles, we'll draw them separately, A, E, B, and then our larger triangle, A, C, D, that we have angle similarity going on here. Really we have angle because they share this angle A, and it must be the same angle measure. Cool, so we've showed that they're similar. That's neato, that's not new. We've done this before. Let's fill in the rest of our information real quick. This is 9 plus 12, so that's 21, and this is 15 plus x. Cool. Well, the key takeaway from today is, well, let's solve this the way we know how. Well, let me take a step back. Let's solve this the way we know how. We're going to set up a proportion here. So this side corresponds here, so we're going to do, I like to do the bigger number on top. So I'll do 21 over 12 equals 15 plus x over 15. And I'll definitely need a calculator for this one here. I want to point out the 15 plus x, where'd that come from? Well, it's the whole side AD. We know that this chunk is 15. We know that this chunk is x. So when you add them together, 15 plus x. All right, cross multiplying. I'm going to do my, I did this, whatever. I'm going to do the 21 times 15, and I'm going to put that result on the right-hand side because I want my x on the left-hand side. So I did 21 times 15 in my calculator, and that's what I got. Over here, it's going to be 12 times the quantity, 15 plus x. Do our distribution. 12 times 15 is 180 plus 12x equals 315. I'm going to subtract 180 from both sides, divide by 12, divide by 1, subtract, yikes, that incorrectly. 315 minus 180, my calculator says is 135. So 12x equals 135, divide by 12, boom, x equals 11.25. Sweet. This is a little confusing though. What if I told you there's an easier way? So today, that's what we're going to focus on, is this easier way, the actual triangle proportionality theorem. So if you run into a situation like this out in the wild, we have a little triangle inside of a big triangle, and the key differentiating thing here is that the two bases are parallel to one another. They must be given that they're parallel. You must be able to show that they're parallel. We can use what's called the triangle proportionality theorem. So we can really just use these two numbers as well as these two. We can set up a ratio, 12 over 9 equals 15 over x. So it's a whole lot easier to work with. So 12 over 9, again, coming from AB and BC. And then we'll do 15 over x. This one's, like I said, much easier to work with. 12 times x is 12x. 9 times 15 Gosh, 9 times 10 is 90, 9 times 5 is 45. Add those together, you get 135. Notice we got to the same spot that we were at just a moment ago, so we're going to get the same solution here. When you divide both sides by 12, we learned that x equals 11.25. So we got the same result here, but the second way we did it was a little bit simpler. And this is using the triangle proportionality theorem. The first way wasn't using any theorem. I was just using the ideas we've discussed previously, but this is a bit of a shortcut. Again, you can use the shortcut, triangle inside of a triangle, two parallel bases. Now, the goal here is to solve for AD, remember. This x is 11.25. That's fine and well, so that's that chunk right there. So we're going to do 15 plus 11.25. Well, 15 plus 10 is 25. Add one more is 26. So 26.25 is our final result here. Okay, I've said it a bunch of times, but again, recap. If you have a situation like this, a little triangle inside of a larger triangle, bases are parallel, you can use the triangle proportionality theorem. I chose to do 12 over 9 equals 15 over x. You could have done 9 over 12 equals x over 15. Cool. That works as well. You can also do it the long way if you don't feel like you want to remember this special case. That's fine as well. Okay, triangle proportionality theorem. Check out some practice problems. Let me know if you have questions. You got this.